what is EMT simulation, right? So let's answer one by one and jumping into the topic. And I guess like I have given an answer directly. So we'll discuss more into this. Basically, at the high level, power system studies can be classified into steady state analysis and transient analysis. What is a steady state? When you're studying the system, not really with respect to time, with respect to a state which is stable, then probably means what say that is steady state analysis, right? Like I am assessing the performance of the system with respect to one instant. That's a steady state analysis. What is transient analysis? When I am studying the behavior of the system with respect to time, then it is a transient analysis. Or I am seeing how the system behaves with respect to some disturbance or some events with respect to time, then that is a transient analysis. Transient analysis further classified into electromechanical transients and electromagnetic transients. Let me go back to this previous slides, but like before that, like let me ask this question: are you clear about what is steady state analysis? Steady state analysis analyzes the performance of a power system with respect to one particular instant, or this is not really going to study any parameters with respect to time. When we say 100% voltage, it's 100% voltage. It's not really going to see how this voltage is changing from 100 to 100.1 or 100.2 or 99 in the next moment or next second, next minute, next hour. So it's not really going to check or analyze any of the system with respect to time. When you are talking about transient analysis, if the breaker opens or if it happens, I mean, so how much time the breaker is taking to open, etc., etc. If you want to study that with respect to time, then it is transient analysis. If you are assessing any system's performance on a single moment at an instant, then it is a steady state. With respect to time, if you are studying, then it is a transient analysis. After talking about this transient analysis, we have to talk about two important transients. I mean, so say whether it is an electromechanical transients or electromagnetic transients. Let's first talk about electromechanical transients. What is electromechanical transients? So when we are studying the interaction between electrical and mechanical, when you are studying the relationship between electrical and mechanical, when I say mechanical, this is the terminology which could be related easily with the physical generators, more specifically like this turbines, right? Gas turbine or a steam turbine. When you have a turbines, like means the interaction between the electrical system, which is transmission lines, cables, right, loads, transformers, etc. And if we are discussing the interaction of this electrical system with the mechanical system, which is predominantly a turbine, right, then we call it like an electromechanical transients. Or like simple example, if there is a fault in a three-phase overhead line, how the generator rotor oscillate with respect to other generator comes under electromechanical transients. What is electromechanical transients? It's studying the transient between electrical and mechanical systems. This is more specifically applicable for like means for say where you want to study the system with a time step of few milliseconds. Say example, there is a three-phase voltage fault in 400 kV system, and the fault lasts for maybe 100 milliseconds, and you are trying to study the relative angle of various generators for 10 seconds or 20 seconds. That comes under means what's the electromechanical transients. So electromechanical transients, what's the example I have given is rotor angle stability, right? So electromechanical, it can be further classified to many things, but like what I have talked about is one example, that is rotor angular stability. What is voltage fault? Voltage fault is the fault which happens without any fault impedance. Means for say R phase falling on a tree, R phase conductor is broken and falling on a tree is fault with the fault impedance of the tree. If R phase is touching Y phase, or R phase is directly falling on the ground without any fault impedance, then that is called voltage fault. Probably refer IEC 60909 for the right means to say definition. So now coming back to then, like, is there any electromechanical transients apart from this angular stability? Answer is yes. voltage stability, LVRT study, HVRT study, frequency rate through study, whatever we are doing, all comes under electromechanical transients. So which means predominantly we know some power system simulation softwares, except PSCAD. If you take almost all other simulation software, like whatever you meant, Neplon, SKM, EC Power, ETAP, MyPower, PSSE, all the simulation software are basically used to perform steady state analysis and electromechanical transients. PSCAD is electromagnetic transients. So steady state, we are clear. I mean, so say we are studying some, or we are assessing the system at one instant, that is a steady state analysis. If you are assessing a system and its performance with respect to time, then it is a transient analysis. Transient analysis is classified into electromechanical transients and electromagnetic transients. So electromechanical transients talks about the interaction between the electrical system and mechanical system. And this deals with like angular stability, voltage stability, low voltage right through studies, high voltage right through studies, etc. And when it comes to the electromagnetic transients, it's an interaction between electrical system and magnetic system, electrical system and magnetic system. And this is basically talking about, interaction, as we told, it's interaction between electrical system and magnetic system, not the mechanical system. And the interaction between electrical and magnetic system happens probably in microseconds, right? So if you take an example of lightning or a switching, the event happens and the lightning happens with probably 1.2/50 microseconds or 8/20 microseconds, right? So the time, total duration of the time itself quite less. So what's the time step which you need to use is like very, very small. Electromechanical transient, the event happens in few seconds. So if you are putting the time step as a milliseconds, it's good to go. When I'm studying, suddenly the generator load is disconnected. What's the rise in frequency? If you want to check, I need not run the simulation with the microseconds or a nanoseconds timestamp. If I am running with some few milliseconds, that's good enough. But if I am running a lightning study, when there is a lightning strikes on the overhead line, ground wire, what's the rise in voltage on the tower? If I want to study this, I cannot probably use a time step of maybe 0.01 milliseconds, because the entire lightning waveform itself like 1.2/50 microseconds or 8/20 microseconds. So electromagnetic transients is used to assess the performance of the interaction between the electrical system and magnetic system, and the time step for this is in microseconds. Whereas electromechanical transients, the time step is in milliseconds. Like power system analysis, basically classified as like steady state and transient. So transient further classified into electromechanical and electromagnetic. First, let's look at and try to understand what are the steady state analysis. So when you talk about a short circuit, you can perform short circuit studies in steady state, or predominantly what is a short circuit study which you are performing using ETAP is a steady state, right? It doesn't mean we cannot perform a short circuit study in transient. We can perform short circuit studies in transient also. We can perform transient also. Like there is something called a steady state short circuit and a transient short circuit. And if you are using IEC 60909, that's a steady state. If you are using IEC 61363, then it is a transient short circuit. What's the standard which you have used for a short circuit? Ask yourself a question. So when you're using IEC 60909, that's a steady state short circuit. And if you're using IEC 61363, right? Let's probably Google it, IEC 60909. Right? IEC 60909 is an applicable for a short circuit calculation, short circuit current calculation in low voltage 3-phase AC system and high voltage 3-phase AC system operating at 50 Hz or 60 Hz. So this standard probably talks about performing a short circuit studies under a steady state condition. There is another standard IEC 61363. Like this is a transient short circuit, and probably obviously if you Google it, like there is something called IEC 61363 versus 60909. You can probably ask yourself a question: what's the difference between these two? Answer: one is a steady state short circuit, and other one is means what say transient short circuit. So let me tell this question to make it clarity why I call short circuit study under 60909 as a transient. Why not as a transient? Why it is a steady state study, right? We think that means was a short circuit study to an extent, like many people also put it as transient, because short circuit event is a transient. That's the reason why like we thought short circuit study could be a transient. Let me ask this question: if you have performed short circuit studies in ETAP using IEC 60909, by any chance, by any time, is it possible to change the instant at which the fault has occurred in the voltage waveform? Let me repeat my question. By any chance, have you able to change the instant at which the fault has occurred? What I mean by that, like in a sinusoidal wave, like is there any place, like means was the voltage, the fault occurs at the maximum voltage, the fault occurs at the minimum voltage, or probably means what it is a negative maximum, etc., etc. So when you are doing ETAP, when you are performing a short circuit study, you will not be able to change the instant at which the fault has occurred. What I mean, let's put sinusoidal wave just for the clarity. Whether the fault occurs at this instant, or whether fault occurs in this instant, whether fault occurs in this instant, or whether the fault occurs in this instant, you will not be able to change that when you are performing a short circuit studies using ETAP. Let me put it here for a better clarity. Okay, this waveform is not really good. Let's probably pick it up. Maybe another good image. Let's try to get some other good image. When the fault occurs at this zero instant, or when the fault occurs at somewhere here, or when the fault occurs at the maximum value, or when the fault occurs at the negative max, or when the fault occurs at somewhere here. First question, let's ask: do you think that means if the fault occurs at a different places of the voltage, this assume that this is a voltage, and like in order to complete one cycle, like voltage will take 20 milliseconds if it's a 50 hertz waveform, right? If it's a 50 hertz, it will take 20 milliseconds to complete. My question: voltage is zero, voltage is at max, voltage is neither max nor minimum, voltage is negative max, again voltage is on the negative, but it is neither maximum nor minimum. So means what say, if the fault occurs at a different instant, 5 different instants which I have given, do you think that the fault current will be different? We need to ask maybe one more question: what short circuit current we are asking about? Are we talking about IK double dash, or are we talking about IDC, or are we talking about steady state current IB? So when we are performing a short circuit studies, what are the different currents which we will find out, right? Like previously I have asked one general question, you have told different, somebody has told the same. So now I am asking a question: when you are performing a short circuit study, what are the different currents which you need to find out? What are the different currents which you want to find out? So if we are a beginner, or probably if you are not aware what are the parameters to be identified for a short circuit studies, then I strongly recommend another YouTube video which you should not really miss. That is the short circuit studies, right? That's, I guess, like a first video which we have probably put it in our YouTube channel. I'll just put the link in the chat. So you just go and watch, you can understand what is the IK double dash, that is initial symmetrical RMS current. What is IDC, that is DC current. What is IP, that is a peak current, right? What is a steady state current, right? Few people call that as like ISS, right? All right. So you will understand all these things. So irrespective of the instant at which the fault has happened, the steady state current remains same. All other currents will be different, including IDC. DC component also will change with respect to the instant at which the fault has occurred. So the DC fault current will change, your asymmetrical current will change, which means the entire wave shape of the fault current itself will be different. After the system settles down in a steady state, which probably takes few seconds, which never happens in the reality, because much before that your protection system have cleared the fault. Steady state value is a theoretical value which never happens in the practical. The system in practical, when there is a fault, your protection system isolates the fault in the transient region itself, not really in the steady state. If you allow the fault current to reach a steady state value, much before that your equipment would have been already damaged, right? You might have designed your system to withstand the short circuit currents not for an infinite time. You might have designed your system to withstand the short circuit current for a specified time. Like for example, transformers, the transformer withstand the through fault current for 2 seconds. Switch gears, 1 second or 3 seconds. Cables, maybe 0.1 seconds, 0.25 seconds, 0.5 seconds, depends upon what's the sizing criteria which you have selected. So each and every equipments in the power systems are capable of withstanding the fault current only for a definite time. It's not for an infinite time. If that's clear, just put CC in chat. If that's clear, like power system is designed to withstand the short circuit, but not for an infinite time, for a specified time. And the specified time is like 2 seconds for a transformer, 1 second or 3 seconds for a switch gear, 0.1 seconds, 0.25 seconds, 0.5 seconds, whatever it is for the cables. Right? And if the fault has occurred, to reach the steady state value, like the system will take a lot of time. The time constant of like TD, right? You might be talking about TD not double dash TD dash TD, like the time constant TD, like much higher than the withstand capability of the system. So steady state value is just a like a theoretical number, which is of no use as far as the practical is concerned. All right, now coming back, which means my symmetrical current, okay. But like if we talk about my asymmetrical current, my DC current, my peak value, all these things will change with respect to the change in the instant at which the fault has occurred. Now let's ask another question. In ETAP, when I am doing a short circuit studies, we told like we are not really selecting the instant at which the fault has happened. And when we are changing the instant at which the fault has happened, the fault current is changing. Is it not like raising a question that then like ETAP results are not acceptable? We told like when we are changing the instant, of the fault current is changing. When I say fault current, IK double dash, that is initial symmetrical RMS current is changing. And we are talking about IB asymmetrical, which is changing. IDC with respect to time, that is changing. All these things are changing. When these values are changing, my question is, means what say, why in ETAP we are not performing the short circuit studies with respect to different instant at which the fault has occurred? The answer is quite simple. Our objective of finding out our objective of performing a short circuit studies in ETAP is not really to find out what's the current is, but instead, like our objective is to find out what's the worst case is. That's as simple as that. We are just looking at the worst case. So means what say, we are just looking at the worst case. So if we are able to find out the worst case, then we need to ask this question. Worst case, is it a maximum value or is it a minimum value? When we say worst case, is it a maximum value or a minimum value? It's both, in fact. Worst case, when we say maximum might be worst case for selecting the switchgear rating. Worst case might be selecting for the cables. Worst case might be for sizing the CTs. Worst case might be maximum value for many other studies. But like the worst case could be minimum also. The worst case could be minimum for your other studies like harmonics, for maybe like what else? To check the sensitivity of the protections, right? Like, so you have to probably think about like both extremes, but like predominantly we are performing a short circuit studies to understand or select the right switchgear rating. Hence, maximum case is enough, and ETAP does that, and we are happy. And if somebody says ETAP result and the real time means to say the fault has occurred, the fault current and the what is the simulation is not matching, it will never ever match. Let me repeat. Your short circuit current in the real time will never ever match with what's the short circuit current in ETAP. Why? When you are performing a short circuit in ETAP, you have assumed that fault is a bolted fault. You have assumed that there is no network change during the fault duration. You have assumed that the C factor is 1.1. You have assumed that there is no change in type of fault from the starting of the point of the fault to the ending of the fault, etc. These are all not really the assumptions of ETAP, it's the assumptions of IEC 60909. So whenever you are using this assumption, what's the fault current which you got is the worst case or the maximum. And like if you're changing the instant, or if you're allowing the the sources to change during the fault, etc., what you will get is like less than this. So, and your pre-fault voltage may not be 1.1 per unit, and your fault may not be a bolted fault, that might be fault with small fault impedance, etc. So in reality, always the short circuit current will be less than the value which you have calculated in ETAP. You should not say that your calculation is wrong, the actual fault current is different. Means when the actual fault current is less than your short circuit calculated, then it is perfect, because the instant at which the fault has occurred might be different. The pre-fault voltage might be different, pre-fault loading condition might be different. The fault may not have occurred with the without impedance, it may occur with the fault impedance, and so forth. So you should not really compare the results and say that short circuit results performed by ETAP is wrong. You can raise such a question when the actual fault current exceeds, the actual fault current at site exceeds what's the value predicted, or what's the value which is simulated in ETAP. You are simulating in ETAP, you are getting 28 kiloamps, but like when there is a short circuit for the given system, in actual condition reaches like 35 kiloamps, then again ETAP is not wrong. You may not have entered the proper parameters. That means like it's a modeling error which you need to check. But literally what I'm trying to say, when your short circuit current which is identified in ETAP is higher than the actual fault current, your simulation is right. And we are trying to find out the short circuit study, the worst case, just to select the switchgear rating, bus bar rating, cable rating, etc. Nothing else, right? So there will be always a confusion or clarification, like whether simulation will match with the reality, or etc. Simulation will match when you are performing a load flow, and if you are finding out like what's the voltage drop when this much current flows, that definitely matches with the simulation as well as a practical, provided you have done the right modeling of transmission line, right? But like when there is a fault, the fault current in ETAP and the actual scenario will never ever match, because we do not know what's the instant at which the fault has occurred. Right. With that, let's go back to our system. Right. What are the studies which are steady state? That's what pretty much we have asked. Like the studies can be classified as steady state and transient. There are many studies which we thought that's transient, maybe a steady state study. Let me repeat this. We thought many studies are transient studies. Like a short circuit, we thought it is a transient in nature, because when there is a fault, the fault current is changing, etc. But basically, load flow is a steady state study, and that's the beauty of the power system. Power system is the most dynamic system in the world, and we are trying to perform a steady state analysis. Let me repeat my statement. It is a funny part of power system. Power system is the most dynamic system in the world, and we are trying to assess that system using a steady state analysis. Short circuit, as I told, like that's a steady state analysis. Protection coordination is a steady state. R plus is a steady state. Harmonic analysis is a steady state. All this analysis, if you check any parameters, the parameters are not really changing with respect to time. So that's the reason why like this studies are basically called as steady state analysis. Load flow, short circuit, relay coordination, R plus, harmonics, these are all comes under steady state analysis. If the steady state analysis is, and each and every study has different objectives, I'm not really going to go through all, but like this gives an idea like Why do we need to perform load flow? And like the standard is IEEE 399, right? Like the standard is IEEE 399. And like in order to find out the voltage profile, you need to perform load flow. In order to find out the equipment loading, you need to perform load flow. In order to find out the losses, you need to perform load flow. In order to perform power factor correction, reactive power compensation, you need to perform load flow. In order to find OLTC range, you need to perform load flow. In order to find out the generator terminal voltage set point, you need to perform load flow. Contingency analysis, you need to perform load flow. In order to find out a steady state stability of the system, you need to perform load flow. IEEE 399, that's a standard for a load flow. And probably means when you look at load flow, these are all the bullet points which we need to check. Voltage profile, equipment loading, losses, power factor correction or reactive power compensation study, transformer, de-energized tap changer or on-load tap changer is needed. If on-load tap changer, what is the range, what's the minimum value, what's the maximum value, what's the generated terminal set point voltage which you need to give, and what's the contingency analysis, whether the system is steady state stable or not, all those things which you need to find out using load. If you're talking about equipment loading, again, like there are multiple like loadings which are available. Something called available transfer capacity, which is the capacity available in the transmission line or a transformer or overhead lines, overhead cables, etc. What's the remaining capacity which is available, which I can use it for a future loads? That's basically called as available transfer capacity, ATC. What is the continuous rating? What is the short time rating? What is the very short time rating? Ambient temperature and previous loading. Like there could be like multiple factors which influence the equipment loading. All these things has to be taken care of. Similarly, losses. What's the losses in each and every branch? What's the total losses? And if I'm operating in a different configuration, if the losses come down, then recommend a means configuration, optimal configuration where the losses could be minimum. Identify different cases, perform, find out the losses in which configuration the losses is less. That could be the ideal configuration. So it can be used for a power factor correction. It can be used for transformer OLTC range, generator terminal voltage set point, especially for cogeneration plants, contingency analysis, steady state stability. These are all the different outcome of a load flow. Load flow is a steady state analysis. Similarly, for a short circuit, you need to find out a short time rating, like 25 kiloamps 1 second, 50 kiloamps 3 seconds, whatever it is. I guess like few people has also commented like this 1 second or a 3 second, which we are saying for a switchgear. So that means short circuit study. So that means the short circuit study is like time dependent, which means like we are claiming that that's a transient. Answer is no. The short circuit study, which is used to find out the short time rating of the switchgear, is a steady state. Here, like only one instant, that's the worst case instant which we are doing, and we are trying to find out what's the RMS current. Then that's a steady state analysis, and short circuit study is used to find out what's the short time rating of all equipments, 25 kiloamps or 40 kiloamps or 50 kiloamps. What's the making and breaking capacity of the breakers? What's the DC component breaking which is required for the capacity, means for circuit breakers? And like the short circuit study is just not input for a relay coordination, it is an input for harmonics, it's input for a transient, it is input for a motor starting, it is input for an arc plus. So short circuit is ideally an input for all other studies, right? And short circuit study, so far what we have seen is a short circuit study of steady state. Because our objective is to find out the worst case, which is a maximum short circuit current. Then comes to the relay coordination, like standard is IEEE 242. Short circuit, the standard is IEC 60909. Load flow, you can follow maybe IEEE 399. Similarly, if you're coming to arc flash, IEEE 1584. So that's also a steady state analysis. When there is an arc, what's the arc current? That definitely changes with respect to time. But what's the arc flash study which we are finding out is a steady state analysis. That means we are not really changing any of the parameters with respect to time. Harmonics, IEEE 519 2014. What's the what's the voltage harmonic distortion which you need to maintain at point of common coupling? What's the total demand distortion which you need to maintain for the current at point of common coupling? All are like specified in IEEE 519, and you have to meet it. This is also steady state analysis. And coming to transient, we are talking about electrical transients. One is the motor acceleration study, other one is the transient stability. The transient stability is one could be like an angular stability, and others yesterday like what we have talked about. The other is like LVRT, low voltage ride through studies, high voltage ride through studies for renewable plants. When you have renewable plants, talking about low voltage right through or a high voltage right through. So this is under electromechanical transients. And beauty is whatever the power system simulation software which you have tried to use, like ETAP or PSSE or SIME or Neblon, EC Power, SKM, MyPower, like whatever may be the tools which you have mentioned in the chat, all are capable of doing both steady state analysis and electromechanical transients. What is electromagnetic transients? Right? What is electromagnetic transients? We have discussed this is an interaction between electrical system and magnetic systems. What are the studies comes under this? There are 6 major studies which comes under this electromagnetic transients. Temporary over voltage, switching over voltage, lightning over voltage, very fast front over voltage VFFO, transient recovery voltage TRV, ferroresonance. All this comes under electromagnetic transients, and that needs to be performed using some simulation softwares like PSCAD or EMT-PRV. And if you are asking transformer energization, where does it comes? It comes under switching study. Like whenever I'm trying to switch on the transformer by means of closing breaker, that's a switching study. The switching study covers cable energization, transformer energization, transmission line energization, etc. Right? That decides or dictates whether the system needs pulse, point on wave switching, POW, point on wave switching or not. So means when you're closing the breaker blindly, the ingress current of the transformer could be like 8 times, 10 times. That may reduce the life of the transformer over a long run when there is a multiple energization of the transformer. So you can use maybe point on wave switching to minimize the ingress current from each and every event, one event to the other event. Right. So what are the studies under electromagnetic transients? One is temporary over voltage. This temporary over voltage can be performed as a part of electromechanical itself. Right? But since this TOV is performed as a part of electromagnetic, the same model could be used for switching also. Right? So TOV, SFO, FFO, variable VFFO, TRV, ferroresonance, all the studies comes under electromagnetic transients. And one important question which we need to ask, what are the softwares which are available to perform electromagnetic transients? What are the softwares which is available to talk about electromagnetic transients? It's predominantly PSCAD and EMT-PRV. DIgSILENT Power Factory also has the capability to model the system. Like DIgSILENT is the only tool probably which has integrated with RMS studies with an EMT study. So they have 2 models, RMS simulation and EMT simulation. Of course, the model of EMT simulation might be very expensive. So you can understand, like that's the only tool which is available, which has both RMS and EMT in the single software. Other tools like ETAP, SKM, SIME, EC Power, Neblon, etc. It's all probably comes under steady state plus electromechanical transients. PSCAD and EMT-PRV comes under electromagnetic transients. What is electromagnetic transients? Switching study. I am energizing a transformer, energizing a transmission line. I am energizing a cable. Like all these things are probably the electromagnetic transients, right? And this all comes under switching study. So what are the things which comes under switching study? Energizing a transformer, energizing a cable, energizing a transmission line, energizing a capacitor bank. This all comes under switching study. I'm trying to switch the breaker. That comes under switching study. And for that, the system has to be represented in a different way. And lightning means the system has to be represented completely in a different way. Yes, DIgSILENT can do the EMT studies needs. So what is lightning? When there is a lightning strikes the overhead line, maybe ground wire or direct stroke, means how this lightning propagates over the overhead line, means what's the rise in voltage in these substation equipments, that has to be covered under lightning strike. Modeling of even a transmission line is completely different for like our RMS simulation and EMT simulation. Generally means what say we model the transmission line like nominal pi, right? This is how we model the transmission line, nominal pi. But whereas means if you're performing lightning study, the transmission lines has to be modeled much more in details. So you cannot just like that model this line as a nominal pi, because if you not model it as a nominal pi, like means also there is no time, and probably means this lightning wave travels at a much higher speed, like 1.2 microseconds / 50 microseconds. So it has to be modeled in much more detail, phase model, which might be means what say highly complicated than what we need to do. When we say EMT, means what say EMT, electromechanical as electromagnetic, same thing EMT. So we have to be a bit careful when we say electromechanical transients or electromagnetic transients. That EMT stands for both same. And right, coming back here, if you have GIS substations, means what say you need to perform this VFFO studies. You need to study this VFFO studies when you have a gas insulated substations. And transient recovery voltage, if you want to check the capability of the circuit breakers, what's the transient recovery voltage, what's the rate of rise of recovery voltage, what's the voltage across the breaker when the breaker has opened, right? First pole clear factor, you might have talked about something, right? So basically the switching over voltage, lightning over voltage, etc. check the BIL, basic impulse level or basic insulation level, whatever you call, is within the limit or not. Like transient recovery voltage study test the capability of the circuit breakers to be applied for that particular applications. Ferroresonance checks whether there is a ferroresonance or not in the system. So this electromagnetic transient is like much more deeper. And having said that, like we have missed probably a few more aspects. When we talk about the software like PSCAD, when we talk about the software PSCAD, the software helps you to perform this electromagnetic transients, but that's one small portion of it. The PSCAD is capable of doing this electromagnetic transient. Of course, it performs a steady state analysis because the transient event has to be created on the steady state. And then like you can talk about protection, like means to say how the numerical relays are probably manufactured much before that. Like the discrete Fourier transformation algorithm is probably tested in simulation softwares like DIgSILENT Power Factory. If you appreciate a fact like the voltage fault, 3-phase fault is detected like less than 3 milliseconds in a distance relay, and probably this has to be tested using some simulation softwares, more specifically some EMT simulation softwares like PSCAD. So when you talk about PSCAD or EMT PRV, we can classify the learnings in the PSCAD into 3 categories. One is insulation coordination, right? Let me put it maybe in a word or a notepad. When you're talking about PSCAD, you can understand from 3 different perspectives. One is insulation coordination. That insulation coordination talks about all the 6 different studies like temporary over voltage, switching over voltage, lightning over voltage, ferroresonance, VFFO, and means what say TRV. Protection is another aspect which we can talk, right? How to model REF relay, how to model distance relay, how to model differential relay, etc. Like this all probably tested in means what say PSCAD. And the last one we can call it like renewables. Now quite a lot of renewables has been probably populated into the market, and the renewable penetration is quite high. Most of the grid codes are asking you to validate and provide in fact the PSCAD model. So how do you model your solar inverters? How do you model your wind turbine generators type 3 and type 4 wind turbine generators? And how do you perform probably even an analysis for the sake which you take it like harmonic analysis, right? I mean, what say if you take means what say modeling of a transmission line for harmonic analysis itself like different, and probably if you are modeling the transmission line PSCAD simulation software, that's giving much more accurate results compared to ETAP, right? So you can probably classify this into 3 different categories: insulation, coordination, protection, and renewables. And like we having a course, and that course is approximately 300 hours course. The course duration is like 300 hours, which is like 150 hours sessions where we explain theory, we simulate, we show how to model, etc., etc. Plus 150 hours hands-on where you are allowed to practice and come up with the questions. So this is the course which we are offering. And if you're asking me what is the course fees will be $1,000 or 75,000 INR. Course fees is like $1,000 or 75,000 INR, right? And like you will not really like we will want to check it because you cannot probably go deep into this. You cannot really go deep into this unless otherwise you understand probably the studies which we have talked about here, right? So you need the basics. This is not really for the beginners. I mean, for say, even we will not really recommend you to burn your money. Once you register, probably we will be having like maybe 1-to-1 call because you are making an investment. We will first identify you whether you are right fit for this course or not. Then if you are right fit, then probably you can register for this course. And the course fees, like I have already told you, it's $1,000 plus 75,000. Means was it this course we are using PSCAD. PSSE is not really capable of performing electromagnetic transients. What's the course which we are talking about? Is PSCAD. PSSE is an RMS simulation tool. It's not an EMT simulation tool. Only PSCAD or EMT-PRV are 2 different EMT tools. I guess like that's pretty much clear. PSCAD or EMT-PRV, and to an extent, DIgSILENT Power Factory has its capability. But PSCAD and EMT-PRV are the competitors, and like they're probably ruling the world of EMT simulation. When I say EMT, performing this TOV, SFO, FFO, VFFO, etc., etc. In addition to that, probably the protection and the renewables, right? So this covers complete grid compliant studies for renewables, modeling and development of protection devices like distance differential relays, etc. So the course is only on Saturdays and Sundays. The course duration is 1 year, maximum 1.5 hours per day, Saturday and Sunday, 3 hours a week, 50 hours course, 150 hours session where we demonstrate theory along with the simulations and stuff, plus 150 hours where you are expected to practice and come up with the assignments and stuff. The total duration of the course is like 300 hours. Cost is known, and I guess like I am done. Maybe along with the session, like I have also made it very clear what you will get as a part of the course, and like that link is only for registering to get a clarity, not to make a payment. Of course, when you have to make a payment, we'll ensure that whether you are right fit for the course, and like we don't want to also have like quite a lot of participants for the course to have like means for say, because we want to put up an attention for the individuals, and like in case if needed, like later we will start the second batch.